Hello, welcome to another video in this series on quantum coding. So in the previous video, we actually coded on an actual quantum computer and ran it there. Rather, we coded on our system and then ran the code on a quantum computer and made an entangled state. And we did all sorts of cool things like measuring it and seeing that these are actually entangled or not. So, um, so that's that. But now we will get into some nitty-gritty of quantum computing. So in the previous videos, we had seen properties of quantum mechanics, but now we will shift gears a bit and focus on the tools or the methods we need for quantum computation. So for regular computer systems and not OR gates, these form the building blocks of everything. Similarly, um, gates in this quantum computing realm are called quantum gates, and we will deal with them. We will start with what do they represent and how does it work and some examples of them. So, so again, like the next three videos will be a bit more theory leaning. I promise that I will keep it to a minimum, but we still need to get some understanding of these things to understand complicated algorithms. So let's jump right in. So in this video, I will talk about um, quantum gates that act on one qubit, and then in the next video, I will talk about physical meaning of quantum bits, like because quantum bits have these complex numbers. So how can I give a physical understanding of it, and that's through a 3D sphere. I will again talk about it later. And then third video, I will basically go over two qubit gates. And I think with that, we should be ready to jump into the first proper quantum algorithm. All right, so lots of learnings to do till we get there. I have my beer, so let's begin. Great. So first of all, let's look at this. Um, any quantum state, you would mathematically represent it as a matrix. So the state zero can be represented as this 2 by 1 matrix, and the first bit is 1, and the next one is 0. And again, the state 1 could be represented as 0, 1. So mathematically, this forms the basis of all 2 cross 1 matrices. So that's why that's the mathematical term for it. But then don't worry about it. Just this is the representation of 0 state, and this is the representation of 1 state. Now, a regular qubit is in a superposition of 0 and 1, which is alpha times 0 plus beta times 1. So you would represent it like this. And this is pretty straightforward. You multiply alpha to this one, you multiply beta to this one, and then because there's an add, you add them up, and this is what you get. So this represents the most general quantum state in this matrix form, which is just a representation. All right, so now let's look at some more examples. So this state, 0 plus 1, where both 0 and 1 have the factor of square root 2, 1 over square root 2, would be a matrix of 1 over square root 2, 1 over square root 2. This state, 0 minus 1 over square root 2, would be represented by this particular matrix where the first element is 1 over square root 2 and the second element is negative 1 over square root 2. Now these two, why did I single out this example, is because these are pretty important and they will come later down the line quite a lot. So that's why they have been given a special designation, the plus and the minus state. So that's why. Now, just jumping ahead a bit. So 0 and 1 form the basis. Like, so everything can be built on 0 and 1. A quantum state has these two building blocks, and on top of that, it could be any combination of these two. So they represent the basis. So, for example, what does the word basis mean? Um, a 2D plane is for a 2D plane, the basis would be the x and y directions because given those two coordinates, you can identify any point, right? So the minimal amount of dimensions you need to explain any space is the basis, or to pinpoint a point in any space is the basis. So plus and minus are again two orthogonal states, and these are a different representation of bases. So these are as good as 0 and 1. So this is a different way of writing the basis states. If this explanation went over your head, don't worry too much about it. Just think of this as some peculiar state. All right, that's all that matters. Now, quantum gates, just like classical gates, which are and, not, or, and all that jazz, are basically matrix operations on states. So they're basically matrices that multiply on a state. Physically, they correspond to certain operations. We don't want to get into that, but then mathematically, all they mean is matrix multiplication on states. So some fundamental gates. Let's talk about some fundamental gates, which are known as poly gates, and these come from, again, this is an aside. These come from the SU2 poly matrices, which basically form the group of rotation of a sphere. So that's where the sphere terminology comes in, and I will talk about that in the next video. So just don't worry about all of that. But then these are, you can say, the building blocks or the building block gates. There is the X gate, 0, 1, 1, 0. There is this Y gate, which has some imaginary numbers. So this is minus I and this is I. And there is Z gate. Now let's look at the action of, say, one of them, X gate. So when X acts on 0, it flips it. 0 becomes 1. When X acts on 1, 1 becomes 0. So this is the flip gate. So X flips the bit. Let's look at this operation in detail. So like I said, the action of the gates on my qubit is just matrix multiplication. So the X gate is 0, 1, 1, 0. I write it like this. And the 0 state is 1, 0. When I perform the multiplication over here, I get 0, 1, which is state 1. And the same would happen for this operation as well. So the job of X gate is just to flip the bit. So this is one important gate. There's a more general gate. There are more representations of more general gates called the U gate. The only criteria gates need to satisfy are that U times U, say if you have a gate U times U complex conjugated, or should be transposed and conjugated, should be equal to identity. So there are more general gates available as well, but then again, I'm skipping over that. So another important one that you will see quite a lot is this Hadamard gate. I hope I got the spelling right. So and this gate looks like this. And what it does is it takes the 0 state to make it the plus state, and it takes the 1 state to make it the negative state. So plus and negative states are these. So that is why I said 0 is equivalent to plus and 1 is equivalent to minus, because action of Hadamard gate takes from 0, 1 basis to this plus and minus basis. And you will see Hadamard gate quite a lot. All right, so I think this is all the theory that I wanted to talk about in this video. So let me now directly jump into code. So how do you represent these gates? So let's see. Let me bring up my notebook. All right, so I have already written out the code, so I will just walk you through it and run it. Again, this code is available on my GitHub repo, and the links for that are in the video description, so please check it out. And also, please like and subscribe, because I want my channel to grow so I can make more cool things. So if you liked it, like and subscribe. All right, so let's jump in. So first we import everything we need. Well, we don't need the visualization, so let's get rid of that. We import Qiskit, And I do not want to run my code on the quantum computer because we are just trying out very simple things. So let's just get a simulator running because I just want to execute it on my system. Right, so let's first implement the X gate. And the way I implement the X gate is I first create, in this line, I first create a quantum circuit of 1 qubit. And I initialize it, let's say with state 1, because alpha is 0 and beta is 1. So this is state 1. Now, this command just initializes it to this value. And if you don't remember, all these commands are executed sequentially. So if I put X above initialization, then after the X gate, the initialization step would act. So all these commands need to be done in the precise sequential manner in which you want the circuit to be executed or circuit to be built. So first we want the initialization. That's why I type it out first. Next, I want the action of X gate. So you can add an X gate by just simply typing out .x, your circuit.x, where circuit is a quantum circuit object. And then as an argument, you need to specify which qubit. We only have one, so I specified its number, which begins with 0. And then I just specified that whatever we have, just measure everything and then draw out the circuit. So here you can see I have initialized it to state 1. I have an X gate, and then I will measure it out. Now, what should happen? X gate is supposed to flip my bit, so that my measurement should be 0. So let's try it out. Here I have the same code that you might have seen it before, which basically transpiles the code for the simulator and then runs the simulation and gets the results out. So instead of plotting it out, I'm just printing out the numbers that I see. And this simulator by default runs 1024 times. So let's print it out. All right, so we get 0 all the times because X gate flips the bit. So what was 1 would now become 0. And that's what we expected. Let's try it again. This time, let me supply it gate 0. So alpha is 1, beta is 0. I specify it and I run my simulator, and you see we get 1 because 0 got flipped to 1. So that's awesome. Similarly, we can apply the Z gate. The action of Z gate doesn't change the state. So again, I have the same circuit as before. Instead of X, I've replaced it with Z. So you can also try it out. So here I have X state over here. And when I measure it, I get X state again, the 0 state back again. So Z doesn't really change the state. But it does something subtly different, which I will talk about in the next video. The thing is, like, these states live in a complex space. So I cannot draw a 2D graph and talk about it because they live in a three-dimensional space kind of fashion. So there's an extra hidden dimensions a qubit has because of its complexity. So I will again get into it in a later video, or rather the next video. Finally, let's talk about the Hadamard gate. Again, the code is as before. Instead of X, I have the Hadamard gate, which is just .h. And you can see my qubit and then the gate, and then I'm performing the measurement. So what does Hadamard gate do? It takes 0, makes it into the plus state. And if you don't remember, the plus state is a mixture of both 1 and 0 with the same probability. So if I run this state, it would become 0 and 1 with the same probability. So when I run it, and you can see both of 1 and 0 come with roughly the same number of times. The measurement is the same number of times roughly. Same should happen if I run it with the state 1, and boom. There is a slight difference. It's because it's a simulator. And again, even if you run in a quantum computer, there would be difference because it's like a coin toss, right? Like if you toss a coin 10 times, it doesn't mean, just because the probability is half doesn't mean you're going to get 5 heads and 5 tails. It's sometimes going to go one way or the other a bit. So, but more or less, these numbers are equivalent, and that is what I wanted to show. So, in this small notebook, which again is uploaded on my GitHub page, you can see how to play with one qubit gates. There are more of them. You can again look them up in Qiskit documentation, but then I think for now we only need these. And I will talk about more complex gates as and when we need them. We don't need them right now. So I think that's it for this video, and I will see you the next time with the next video. I'll just talk about, won't particularly be about coding, but it will be more about this representation of qubits and how to physically make sense of this action of gates. All right, so I hope you enjoyed this short one, and if you like this video, please comment below, please like it, tell me how I am doing, and yeah, and I will see you in the next video. Bye.